So one more thing that we can do is to simplify these things down, we can write these equations in terms of their sort of dimensionless equivalent. And so why would we want to do that? What's the value? Well, let's say we go to all this trouble, we have this system of equations and we have maybe a problem that we care about. It's maybe flow over a flat plate or flow over a cylinder or something like that. And we go through and we solve that problem we solve the system of equations for that problem. Wouldn't it be great if we could have that solution apply no matter what our density was or no matter what our velocity was? Right? So could we sort of collapse solutions down to a single base solution that is the solution for the normalized equation, and then go back and apply it to dimensional equations later? So the goal is let's use these equations, let's really express them in terms of their dimensionless equivalent, and then we'll use those to develop correlations that we can actually use in practice. So there's two ways to go about doing this. One, you probably remember who had what's it called, Buckingham pi theorem in fluids. You guys seen that? Okay, most of you. So if you remember that, basically what you do is you say, I'm going to guess 3 or some handful of properties that I think are important for this. Maybe viscosity, maybe density, maybe specific heat for a given thing that you care about. And then you find a way to arrange those parameters so that they produce a dimensionless coefficient. You substitute that in and then you go through. So it's one way to do that. It's kind of an arbitrary thing though. So it turns out actually what we can do instead, which is our second option, is take the independent variables or dependent variables in this problem, so like velocities or temperatures, and normalize them with respect to some meaningful normalizing quantity, and then go through, substitute that in and walk through the entire process. And what you find is that as you go through that at the end, you're going to have these terms left over that are sort of multiplying parts of your equation, and those end up being your non-dimensional thing, like your Reynolds numbers or your Reynolds numbers. So let's go through and do that. Again, there's nothing especially difficult about this, but it's worth seeing how it's done because it leads to a lot more stuff. So, okay, so here's our differential equations. So let's go through and decide what variables we want to normalize this. So first, what are the variables that are appearing here? We have, let's say we have X, we have Y, let's see, we have U, we have V, right, our two velocities, and then we have a temperature, and we have a pressure. So we need to figure out how to normalize every single one of these 6 things in order to write our equations in terms of those dimensionless or normalized values. So the first thing let's do is let's come up with an equation for X. So how would we normalize X in this problem? Yeah, or divide by it, right? So X, so let's call X normalized, X hat or X tilde. That would be X divided by L. So then the entire problem is going to exist between 0 and 1 in the X coordinate. For Y, so what's our dimensionless Y going to be? This one's a little tricky because you don't want to normalize by, say, the boundary layer thickness because that's changing. So let's just pick the same thing. Let's say it's Y over L. So that's our coordinate. Our velocity U. So if we normalize that, what would be a good normalizing thing there? Yep, free stream velocity would be good. V. So this would be our Y component velocity. Let's also do that by U infinity. Okay, and then temperature. So how do we normalize? We've done this a little bit before, but what's one way to normalize temperature, keeping in mind that you don't want to just divide by some reference temperature? Yeah, right. So temperature you're at, T, that's changing minus some base temperature. So what's the lowest temperature in the system? That's going to be T infinity. What's the highest temperature in the system? It'd be TS, the surface temperature. minus T infinity, and we'll call that theta. So theta is going to be our normalized temperature. Again, this is going to always, for this problem, be between 0 and 1. Okay, pressure. So our normalized pressure, this one's a little tricky too. You don't want to just divide by some reference pressure because the pressures, just like temperatures, the pressures in the system can be relative to kind of anything. So for this one, actually, what we want to do is normalize by the fluid momentum. So rho u infinity squared, something close to the fluid momentum. Okay, so we have now these 6 different normalized representations of this variables in this problem. And then the next step for us is just to go take these, substitute them in, right, and then re-express the same equations that we had before. Right, and when I substitute them in, what am I going to do? So here we would say x, when we make the substitution, it's going to be x is equal to x tilde times L, right? Y is y tilde times L, and so on. The other one that's a little tricky is here we'd say T is equal to theta times Ts minus T infinity plus T infinity. Right? That's the thing we're substituting in for the variable as we go through. Okay, let's go do that then. So we'll start with the continuity because that's the easy one. So this equation is what? It's du dx plus dv dy is equal to 0. So we need to make our substitutions here. We'd say here this u is going to be u is equal to u tilde times u infinity. This v is equal to v tilde times v infinity, u infinity. You write that? U infinity. Let's see what else. Here x, so x is equal to x tilde times L, and y is equal to y tilde times L. Right? So we go through and we do that. We just have to directly substitute those things in, and we end up with, as you could guess, it would be the partial of u tilde times u infinity divided by partial of x tilde times L plus partial of v tilde times u infinity over partial of y tilde times L equals 0. Okay, so let's see. We can go through, we can pull out our u infinity. That's a constant. So that's going to go away. We can pull out L. That's a constant. So then our simplified non-dimensional equation is just d u tilde dx tilde plus dv tilde dy tilde is equal to 0. That's our normalized equation for continuity. Questions on that? Okay. Yeah, right. So v is a function of x, where u infinity is like a constant, something fixed about the problem. Okay, let's go next to, let's see, x momentum. So x momentum, we have to do the same thing. So here's our x momentum equation. We're going to substitute in. So let's write this out. We have, what just happened? So we have rho in front. So substituting in now u, right, we have u tilde u infinity times the partial u tilde u infinity with respect to the partial of x tilde times L plus v, so that was v tilde u infinity times partial of u infinity, or u times u infinity over partial of, let's see, y tilde times L. Partial of u tilde u infinity over partial of y tilde times L. Okay, and then, so that's the left-hand side. And then see that equals, what's on the right-hand side is going to be minus d of our pressure. So what's our pressure? It was P let's see, what did we say that was? So this is PPP. So this P here. So this is going to be the free stream pressure. Okay, so I guess in this derivation, what we're doing is we're going to make an assumption for this derivation that the geometry we have is a given geometry, is some fixed geometry. Okay, if we do that, then we can make this substitution where we call this pressure. We say that this pressure is basically fixed. Okay, and that ends up giving us the expression as follows. So this is P infinity. Let's see, normalized P infinity times rho times U infinity squared. So that's all in the numerator, and then divide that by dx tilde times L. So this up here, it should be, why does that? Sorry, I'm basing this derivation off the book, and if I was doing it, I'm not sure I would have labeled that P infinity. So let me actually, let's do it the same way as the book for now. I'm going to come back to that. I'll clean that up next time we talk. Okay, so let's just continue on here. We have that term, and then the second term here is, on the right-hand side is mu times the second derivative, so d squared of u tilde times u infinity divided by the derivative y tilde times L, right? And that's, I'm sorry, just the denominator squared there. Just the denominator squared. Okay. Hopefully we got through that okay. So we have all of our normalized stuff here. We substituted into X momentum. And then we can go through and start pulling stuff out. Okay, so we have, let's see, on the left-hand side, we have rho times u infinity squared over L. We can pull that out. And then in here, we're left with u tilde, du tilde, dx tilde, plus v tilde, du tilde, dy tilde. And then on the right-hand side, we have minus rho u infinity squared over L times dp infinity tilde divided by dx tilde. Right? And then the second term was plus mu u infinity over L squared times the second derivative d squared u tilde divided by dy tilde squared. Okay. So there's our one step further in simplifying this. But if you look at this, right, we still don't have a normalized or dimensionless equation. We have these terms like the u is dimensionless, the v and y, they're dimensionless, but we have these constants that are multiplying the terms that are not dimensionless. So we have to figure out how to make this equation dimensionless. So what we can do is we can, the units on all these terms should be the same. So if we divide what's multiplying one of the terms by all the terms by what's multiplying one of the terms, then we should end up with a dimensionless equation, right? So let's do that. Let's actually divide everything through by this thing out in front here. So we divide the full equation by that, and we're left with what? What's over here? So just copying this part u du infinity dx or tilde plus v tilde du tilde dy tilde. So that's on the left. And then here we have now divided rho u infinity squared over L. So that first part goes away. This just becomes minus dp infinity tilde over dx tilde. Right? So that's just that term now. And then the last term is the messy one. So this is mu. We have u infinity over L squared. Then we have L over rho u infinity squared times d squared u over dy squared. Okay. What can we see about this, right? We have something here, I guess this term here is kind of our interesting term. Everything else now is normalized. The first, second, third, these are all dimensionless terms. There's no dimensions with those. Here's where all the interesting thing is happening. This is a dimensionless group, right? It has no units, just like the other things, but it's something, right? It's a bunch of constants together. And if you look at it, well, we have what? We have U infinity here. That goes away there. We have an L squared, so that L goes away. So we have mu over rho U infinity L. You guys know what that is, right? That's 1 over the Reynolds number. Okay. And so think about like what we did there. We took, what's this first term, right? This is our momentum term. Okay, we're dividing through the stuff on our momentum term through the entire equation. And over here we have our viscous term. So in the end, we end up with the stuff in the viscous term divided by the stuff from the momentum term. And that's the definition of the Reynolds number, right? So it makes sense. That's sort of how it should go. But in fact, it ends up working out nicely like that.